Here's the answer for page 21. The oral exercise is number 1. We are given a theorem and asked to provide the reasons for the statements in the proof of that theorem. When you look at the first statement, A equals B and C equals B, that comes directly from the hypothesis of the original if-then sentence given in this problem. So the reason for writing that at the beginning of the proof is that it's given information. The next statement is B equals C. The connection of this statement to the one just before is that B equals C is the same thing as this equation, but the left and right sides have been switched. The algebra property that justifies that is called the symmetric property. Now statement 3. What is the justification for saying that A is equal to C? Let's look at the statements that came before. One statement was that A is equal to B, and another statement is that B is equal to C. These statements are connected to each other. A equals B, B equals C, therefore A equals C. It is the transitive property that justifies this statement. Page 22, the written exercise is number 1. We have a theorem. If AC equals BC and C is not 0, then A equals B. Let's prove that that theorem is true. The first statement of any proof is to copy down the information given to you in the hypothesis of the original sentence. The hypothesis is the portion of the sentence associated with the word if. So our given information is that AC is equal to BC and C does not equal 0. The reason for writing that at the beginning of the proof is that's given information. Statement 2. What can we conclude from this equation that we just wrote down? Can we directly conclude the statement that we want to create, A equals B? We can. So we can write A equals B as long as we give a reason. To get from this equation to this equation, what happens is you would divide both sides by C. What algebra property justifies dividing both sides by the same number? That's called the division property of equality. Now for some review. Page 16, the oral exercises. We're asked for the additive inverse of this number. That's the number, but with the opposite sign, so negative 1/3. Then we're asked for the absolute value. That is always the positive version of whatever is inside the bars, so positive 1/3. Number 12. This expression right now is equivalent to 0.8. Now let's give the additive inverse, negative 0.8. Then let's figure out the absolute value. It's positive 0.8. Number 20 asks for the reciprocal of this number. 1.5 is the same as the mixed number, 1.5, because the decimal 0.5 is equivalent to the fraction 1/2. The mixed number 1.5 is equivalent to the fraction 3/2. 2 times 1 is 2, plus 1 makes the numerator 3. Now that we know the fraction associated with 1.5, we can flip it upside down to find out the reciprocal is 2/3. Number 30 is a true or false question. 2 is less than the absolute value of negative 4. Let's rewrite that expression as 2 is less than 4. Then we can see that it's true. Number 34, is this statement true? Can this fraction be dissociated into the product of these two fractions? Yes, it can. That's true. Page 18, solve these equations. Negative of negative t is equivalent to positive t, and that's equal to 1. Number 14, we want to find the negative of what's inside the brackets. The negative of negative 1 is positive 1. The negative of negative y is positive y, and that's equal to 8. From this equation, we can see that y must be 7. Number 12, let's solve this equation. The first step is to rewrite it and replace the absolute value of negative 2 with 2. Then we can see that this portion must be 0. So what number for v would make that turn out to be 0? And we get v equals 0. The next question asks for graphs on a number line. Negative p is greater than 2. If we divide both sides by negative 1, we get that p is less than negative 2. Find negative 2, put an open dot, and shade the numbers less than. Number 22. We can solve for c by dividing by negative 1 on both sides. When you divide by a negative, switch the arrow symbol. c is greater than or equal to 1. Locate 1, put a closed dot, and shade the numbers greater than it. Number 26. The absolute value of x is less than x. Do you see that this is an empty set, that there are no solutions? Because there are no numbers that you can take the absolute value of and get an answer that's less than the original number. Think about it. Does the absolute value of 0 make a number that's less than 0? What about the absolute value of a negative number? Does that make a number that's less than the negative 2? Is the absolute value of a positive number less than the number? None of these are true. This has no solution. Number 28, the absolute value of t is greater than or equal to 0. This is true for all numbers, so you would shade the entire graph. Run through some examples like we did in number 26. What happens if you find the absolute value of 0? Do you get a number that is greater than or equal to 0? Yes, you do. What if you try the absolute value of a negative number? Do you get an answer that's greater than or equal to 0? Yes, you do. What about the absolute value of a positive number? Is it greater than or equal to 0? Yes, it is. We've tried all cases, a negative, a positive, and 0, and every time we found out that the numbers worked. Number 32. Let's solve this compound inequality for f. The variable f is alone in the middle of the inequality, other than the absolute value bars. So the negative 1 and positive 1 appear to be the endpoints. There's no equal to bar on this arrow, so an open dot. There is an equal to bar on this arrow, so a colored in dot. Where should we shade? From the look of the expression, it looks like we should shade in between. But we can check if that's correct by trying a number to the left of negative 1 and seeing what happens. If we chose a number to the left of negative 1, such as negative 5, is it a solution to the inequality? Is the absolute value of negative 5 in between negative 1 and positive 1? No, it's not. So numbers to the left of negative 1 should not be shaded. What about numbers to the right of positive 1? For example, the number 3. Is the absolute value of 3 in between negative 1 and positive 1? No, it's not. So numbers to the right of 1 should not be shaded. Number 33. Solve this compound inequality. We can isolate k in the middle by dividing by negative 1. We need to divide all members of the inequality by negative 1. Negative 1 divided by negative 1 makes positive 1. When dividing by a negative, you reverse the arrow. In the middle, we get the k alone. Reverse this arrow, and over here, negative 2. We are not used to having compound inequalities that have greater than symbols in both spots. So we can rewrite this expression is negative 2 is less than k is less than 1. Do you agree that this still indicates that k is in between negative 2 and positive 1? Now we can make the graph. Negative 2, positive 1, open dots on both, and shade in between. Last question. Again, we can get the variable alone by dividing by negative 1. Divide all members by that number. We get negative 2 is less than or equal to h, which is less than or equal to positive 2. Then we can graph. Close dots because of the extra or equal to on the symbols. And the variable h is in between those numbers.